So we're going to talk some about wave behavior, you guys, and the lab you did with the Slinkies the other day kind of introduced you to this concept. And we talked about how waves are different than particles. Some of the things that waves do are also very different than particles. But the first thing I want to talk about is when a wave meets a boundary. And this is kind of like what happened with your Slinky. When you sent a wave down the Slinky, the boundary could have been the end of the Slinky. What did the wave do when it hit the end of the Slinky? It bounced back and it inverted if the boundary was rigid, right? Was it the same size when it bounced back? No. Why not? Energy can't be gained or destroyed. So what do you mean by energy loss? Okay, excellent. So when a wave hits a boundary, some of the energy bounces off, we call that reflection, and some of the energy gets transmitted. And we'll talk about transmission of waves and how waves will refract when they enter a new material. If the boundary is rigid, the reflected wave will be inverted. Okay, it'll switch to the other side of equilibrium. And if the boundary is not rigid, the reflected wave will not be inverted. And just some terminology for you. We talk about the wave that's originally coming towards the boundary is the incident wave, and the wave that comes off of the boundary as the reflected wave. John?
What would be an example of a boundary?
So we talked about when a wave hits a boundary, how it inverts. Let's look at the specifics of that real briefly. Here's a rope with a transverse pulse heading down it, coming to a rigid boundary. You guys know that when it reflects, it will invert because that boundary is rigid. The reason that's happening has to do with the physics of what's going on here. This little particle right there, what direction is that particle moving? That one is going up as the wave pulse approaches. It still hasn't gotten to the crest yet, okay? This one over here is moving down, correct? Yeah. Okay. So as this wave pulse gets to the wall, this part of the rope wants to go up, right? That's a terrible arrow. It wants to go up. You with me? It's attached to the wall. It wants to go up, so it's pulling up on the wall. It's going to exert an upward force on the wall. According to Newton's third law, what's the wall going to do? The wall is going to exert an equal and opposite force in the downward direction on the rope. So the rope pulls up on the wall doesn't move. Newton's third law says the wall pulls back on the rope. That downward pull on the rope causes the rope to start going in the downward direction, and that is why the reflected pulse is inverted in that case. If you don't have a rigid boundary, the reflected pulse does not have that thing to pull onto. Instead, it's just kind of flipping off the end, and it then reflects the pulse back on the same side. What did you guys discover about two wave pulses coming towards each other? When you sent them from opposite directions coming towards each other, what did they do? Pass right through each other. Okay, that is something that waves do, particles don't do. You can't take two baseballs and throw them at each other and watch them pass through each other. Doesn't happen. You can't take two solid objects and make them exist at the same place at the same time. But waves can. Waves will come at each other, pass right through each other. They will affect each other when they are superimposed, when they're on top of each other. But once they pass through, nothing will have changed. And you know this intuitively just by listening to music. We've told you that music is sound is a wave. And when you're listening to a band, okay, for example, you got drummers, you've got bass guitarists, singers, you got all different kinds of musical waves coming from that band. Those waves are able to pass through each other without affecting each other. Imagine listening to music from a band if the sound waves either bounced off of each other or like globbed together and became something different. I mean, it would be insane. It would be totally crazy. But instead, they pass through unaffected because waves can do that. When two waves pass through each other, they do affect each other when they are overlapped, however. And you might have noticed this or not, but basically, the displacement of the wave that gets created when two waves overlap is equal to the algebraic sum of each of the individual waves. For example, here are two wave pulses approaching one another at high speeds. This one has an amplitude of 3 units. This one has an amplitude of 3 units. When they overlap, that moment where they overlap, what will the wave look like? Okay, it will create a larger wave pulse that has an amplitude of 6. After they've passed through each other, everything is going to look exactly the same. They'll go on their merry way as if nothing had ever happened. Okay? What if, similar situation, I have a wave pulse here, but the other one looks like that. They're coming towards each other. Let's say that this one has an amplitude of 3, and this one has an amplitude of -3. What will they look like when they overlap? If they're the same shape, you will get absolutely nothing. Then they will pass through one another, going on their merry way, as if nothing ever happened. Same amplitude, same wavelength, same shape, and everything. If they have different shapes, it's just the algebraic sum of the two. Okay. Hold on one second, Tyler. Let me show you one more. If this is the scenario, let's say this has an amplitude of 3 and this is an amplitude of -1. What's it going to look like when they overlap? Algebraic sum. It's going to be in the positive direction with an amplitude of 2. I'm assuming these do have the same wavelength and everything else about them is similar. The only difference is their amplitude. Okay. They still will interfere with each other if they have different wavelengths. So when waves do this, when waves pass through each other and affect one another as they're passing through, that's called interference. And waves can either they can interfere in different ways, but there's two main ones that we talk about, which is constructive interference and destructive interference. Constructive interference is like that first example we just did, where when two waves overlap and the resulting wave is a larger wave, that would be constructive interference. Destructive interference is when two waves overlap and they cancel each other out. Okay, this is how sound canceling headphones work, basically. They measure the outside ambient noise, they flip the waves, they invert the waves, and then they overlap them on that sound going into your ears, and it basically cancels that sound out. It makes it disappear. Okay. You can do that with speakers as well if you reverse the wires and kind of make that work. We'll talk about this ideas of nodes and antinodes and standing waves in just a little bit when we get into standing waves. So let's practice wave interference here. I've got 3 different scenarios. Let's get scenario A here. I've got 2 different waves. Imagine that they're overlapping each other just like this. What will be the result of those 2 waves overlapping?
Double one.
Okay. And so what would we call that? Constructive or destructive? Constructive interference. Notice that the 2 waves are in phase. Okay, the crests meet, the troughs meet, we call that in phase. Okay, that's the waves are in phase. This one, notice the waves are out of phase. Crests are overlapping with troughs. What will be the result? Zero. Destructive interference. Okay, and this one, they're just slightly shifted. They're phase shifted. So they have the same amplitudes, and what you're going to get, you'd have to do it, Tyler, what you were talking about earlier, where you'd have to like add up each one individually, look at if you're positive or negative. You would end up with still a wave, but it would be shifted out of phase as well. Okay, so that's interference. Okay, so we're going to go visit a little website here that will show you superposition of waves. So we just demonstrated on the Slinky how we create standing waves, where if incident waves reflect off of a boundary and they're coming back, those incident waves and the reflected waves will interfere and create standing waves. Here's an example of a standing wave where the standing wave that's created is half of the wavelength, or is twice as long as the rope that is doing it. Notice that I can create a standing wave where I have 1 complete wavelength on the rope, where I have 1.5. I can make it 2 wavelength, 2.5, 3, 3.5. Okay. The parts that don't move are called nodes. The parts that move a lot are called antinodes. Nodes are regions of destructive interference. Antinodes are regions of constructive interference. Okay. Yeah.
I'm so excited.
Okay. Some websites that we will use to explore standing waves. We've been talking about waves as if they are these kind of singular dimensional things, but we know that waves actually exist out in the real world in multi-dimensions, so we need a way to represent that. When you've been doing things like on your Slinky lab and all, you've been drawing waves kind of like this, like, oh, there's my Slinky wave. Okay, that's kind of a one-dimensional thing. Now imagine this being two-dimensional, where it's extending into the board and out of the board. Okay, so each of these crests would have length to them. If you were to rise above that a little bit, you could draw it kind of like this. I could just draw lines like this for every row of crests traveling. All of a sudden, I've drawn that. I would call these wave fronts, and sometimes we'll draw wave fronts. Have you ever been to the ocean and been up on a cliff looking out over the ocean to see if there's waves coming in? This is what you see. You see these wave fronts coming towards you, these swells coming towards you, and so we can draw those with lines. So sometimes what we'll do when we're representing waves is we'll just do this. Okay, and what that means, each of these lines could represent the crests of the wave fronts coming in a certain direction. To simplify things even further, we'll do ray diagrams where we'll just draw rays, and a ray is really just a line with an arrow. It's kind of nice. The ray should be drawn so that it is perpendicular to the wave fronts as they travel. Okay, so realistically, when we're getting into optics and things like that, we will draw light like this as a ray. There's my light ray. And what that means when you've drawn that is that, oh, there's really light waves that look more like that, and those light waves really should be something kind of like this. Make sense? Simplify the way we draw waves in multi-dimensions. Okay, great. Now, what's that? Why does what happen? Okay, so wave reflection is pretty darn simple. We know that particles reflect. You can take a basketball or a tennis ball or anything and throw it against a wall and it'll come back. That's reflection. Waves do the same thing. How do you know that, what have you experienced that tells you that waves reflect? Okay, yell in a canyon, you'll hear an echo. That's sound reflection. How about with light?
Laser in a mirror.
Laser in a mirror, or even your face in a mirror. You wake up in the morning, you look in a mirror, that's reflection. There's light coming off of that mirror and into your eyes so you can see yourself. And truly, anything you look at is reflection. Okay, you see me right now because light's reflecting off of me and going into your eyes. So we know that waves reflect off of things. The law of reflection is probably one of the easiest laws that you will learn in all of physics, and it basically says that the angle of incidence equals the angle of reflection. Super easy, so easy we probably don't even have it in the equation booklet. But if you're more of an equation type person, we could write it this way. The angle of incidence equals the angle of reflection. God, that is simple. Okay, if the angle of incidence is 24 degrees, what's the angle of reflection? If the angle of reflection is 38 degrees, what's the angle of incidence? 38 degrees, there you go. So very, very simple law. The angle of incidence equals the angle of reflection, but we need to talk about what the heck do we mean by the angle of incidence and the angle of reflection. So that's what this picture is for. Notice now I've got, in this diagram, it looks kind of skewed, but it's actually, once you look at the details, it makes some sense. There are ray diagrams, those are the pink lines, and then there are wave fronts, those are the blue lines. Notice that the angle of incidence is measured between the ray and this line that is drawn perpendicular to the surface. That line that's drawn perpendicular to the surface is called a normal. A normal. Normal in physics means perpendicular to, or 90 degrees. So when we talk about optics and we're dealing with light, we always measure the angle relative to the normal when we draw a ray diagram. Okay? The law of reflection says that the angle of incidence will equal the angle of reflection. Pretty basic. One of the things you might notice here is that it does look kind of skewed here, but if you look closely, it's not. Here is the incident ray, and notice it is drawn perpendicular to the wave fronts, just the way it should be. It is totally an optical illusion because it actually is perpendicular. And if I was to look at a wave front, notice that the angle that the wave front makes with the boundary is exactly the same as the angle that I measure between the ray and the normal, okay? So that's why the angle of incidence equals the angle of reflection. But we usually will just simplify it and we'll say, okay, here's a ray of light coming in, I draw a normal, this is my angle of incidence. I don't bother drawing the other parts usually. Okay? Okay. Have you ever noticed that sometimes you can see yourself in things like mirrors and sometimes you can't? Okay, like this wall right here is orange. There's light bouncing off that wall, but it's orange and you don't see yourself in it. This whiteboard, you can kind of start to see yourself in it. In a mirror, you can totally see yourself in it. So what's the difference? Light's bouncing off of all those things. The material's different. But what is the difference between those materials that allows you to see an image?
One of them's more reflective than the other.
Vacuum light perfectly. Others have like a mirror is like smooth as compared to like.
And that is the main difference, is how smooth they are. So notice here, we've got two different surfaces. And when we look at them at a very small level, one of them's kind of rough and the other one's very, very smooth. The rough one, I've got light rays coming in that are all parallel to each other. When they hit, they go all different directions. That would be like this orange wall. That's why you don't see images in it, because the images get dispersed all over the place. This second one, notice the parallel rays come in, they bounce off, they come off exactly parallel, and you can see an image in it. This would be a mirror, okay? Parallel light rays will stay parallel when they bounce off of a mirror, so the images will stay as images, and you'll see things in it. The law of reflection still holds true. If I look in drawing A, if I look at each of these little light rays, the angle of incidence still equals the angle of reflection, but it's the fact that the surface is rough that changes this. And you might have noticed if you're ever driving at night, and when you're driving at night and the roads are dry, you can see pretty well, it's not a big deal, but when it rains, the roads get wet and it gets much smoother, and all of a sudden there's lights reflected off the road, and stuff gets reflected off the road much brighter because it gets smoother. Yeah. Okay, so wave refraction is the next thing that waves do. As a wave enters a new material, it will change direction if it changes speed, and so that concept is known as refraction, the change of direction at a boundary when a wave enters a new medium. And this can be explained in a lot of different ways. Some people talk about the row of army soldiers technique for explaining this. I kind of prefer the 4x4 Jeep way of explaining it, which goes something like this. Imagine that you have a wheel on an axle connected to another wheel. This will actually be a 2x2 instead of a 4x4. So here's my axle with two wheels. They're rolling along at the same speed. They're going the same direction, which is this way. This wheel will enter the new medium first. You with me? And imagine that the new medium is mud, so that wheel slows down. The other wheel is still in the original medium, traveling at the original speed when this first wheel slows down. So what will the axle do? It will turn until the second wheel enters the new medium, and then my axle is going a new direction. Well, waves are exactly the same way. Instead of an axle, I have a wave front. This part of the wave front enters the medium first, it slows down. This part of the wave front, which is still attached, it's all the same wave front, continues on at the original speed until it enters the new medium, and by then the whole wave front is now traveling a new direction. That's called refraction. Okay? Finish. All right, so let's look at a diagram here. Here's a picture of a light bulb being shined, or a flashlight being shined into water. And notice that we've drawn our waves of light coming out just as a ray. Here the ray bends, as the ray goes towards the water, it bends towards the normal. Some of the light is reflected. We talked about, remember, whenever a wave hits a boundary, some's reflected and some's transmitted. In this case, it bends towards the normal. If I turned around and stuck my flashlight in the water and shone it out, it would bend away from the normal. The reason it does that is because the light is traveling at different velocities. And using the analogy we just talked about of the axles and things, in which material, air or water, will light be traveling faster in this case? So let's think about our axle drawing that we talked about earlier. Here's our wheels traveling along. If it's going to bend towards the normal, is this wheel going to be speeding up or slowing down first? Slowing down first. So the light travels faster in air than it does in water. Whenever you have a wave that bends towards the normal, you know that it has entered a material where it has slowed down. If you have a wave that bends away from the normal, you know that it has entered a medium where it has speeded up. Okay? Sped up. Speeded up. Sped up. Okay? This letter N is known as the index of refraction, and it is a number that tells you something about how fast light travels in that material. The greater the index of refraction, the slower light travels. Okay? The greater the index of refraction, the slower that light travels. What's that? Okay? Willibrord Snell is this guy that lived back in the times of Galileo and Kepler, and he studied refraction very closely. And he looked at the angles of incidence and the angle of refraction and the materials, and he discovered a relationship which we call Snell's law. And what he found is that the angles aren't always equal. Like in reflection, the angle of incidence equals the angle of reflection. But he did find out that if I took this ratio of the sine of angle of incidence divided by the sine of angle of refraction, I would get a constant number for that given material, as long as I was going from air into that material. So that was kind of cool. When he investigated even more, he got a more general law, which looks like this. The index of refraction times the sine of angle of incidence of one material will equal the index of refraction times the sine of the angle of refraction for the second material. This is general. You can be used for anything that light travels through. And again, n is the index of refraction of a material. It is a number that is specific to that material, and it tells me something about the speed of light in that material. The index of refraction for air is 1. Well, actually, for vacuum, it's 1. For air, it's slightly less than 1, but we'll usually just say it's 1. For water, it's 1.33. Those you should probably know. Other ones will be given to you for things like glass or diamond or whatever. And with more investigation, here's what he discovered. The index of refraction is equal to the speed of light in a vacuum, c, divided by the speed of light in that material. Okay? Knowing that, tell me why the index of refraction can never be less than 1.
Because the speed, you can't have a word.
Yeah, nothing can travel faster than the speed of light in a vacuum.
Nothing can travel faster than the speed of light in a vacuum, so the index of refraction will always be greater than 1, okay? Or equal to 1 if we talk about the index of refraction of a vacuum.
So we're use the 1.003 or what?
We use 1 for air.
So they just arbitrarily.
So we've talked about reflection, superposition, and refraction. The last thing that waves do, which is kind of nifty, is called diffraction. And this is unique to waves. Particles won't diffract. Waves will diffract. And the idea of diffraction is that a wave will bend around an object, or it will bend through an opening, okay? As long as the wavelength is large relative to the object or relative to the opening. This again is known as diffraction, and like I said, the longer the wavelength, the more diffraction will occur. What that looks like visually is this, okay? Here are a bunch of wave fronts approaching a wall. Notice that they're nice and straight. Here's a little opening in the wall. Some of these waves are just going to hit the wall and bounce right back. No big deal. If these were particles, the portion of the wave that hits this opening, we would expect them to just continue on in a nice straight line. But waves don't do that. Waves will go through the opening and actually spread out and come out as big circular waves going in all directions. That process is known as diffraction. Again, particles don't do that. The reason they do it because of this thing called Huygens law, and I don't want to get into the details of that at the moment, but ask me again in a second. But imagine, you know, for example, there's some evil person hiding there behind the wall, okay? And you're standing right over here with your big evil person gun, okay? Trying to shoot the evil person, all right? Your gun shoots particles. We call those particles bullets, right? And shoots those bullets. And notice that if I'm shooting particles, I can't hit the evil person because they'll just go through.
But if you have a ray gun.
But waves, if I have some sort of crazy wave gun, yes, my waves will come out and hit the evil person. That is diffraction. Okay? So you can explore these websites to check out more about diffraction.